So this is the times of January 3rd, 2018. The front page didn't have anything. I could have included it. Just there was nothing about this in the front page, but there was again something about Israel in the front page, as we do. But it got a lot of noise. It got a lot of interesting. And attackers found this was actually Spectre and Meltdown. I'm not going to be talking about Meltdown today because Meltdown is, in a sense, it's sort of a bug. But Spectre is a real problem. Now, what is Spectre? To explain Spectre to you, I need to go back to our nice little... Oh, did I put the front page? Did I end up doing it? I need to go back to the Virgulator. So if you remember the Virgulator, let me share the screen with you again. The Virgulator is... here's the Virgulator. This is an emulated microcontroller that we saw. I can run all sorts of programs, and we saw it has a memory, it has a program counter, it has a logic unit which does the calculations, and it has all sorts of it has a bus which connects from one to the other. And if we take for an example this program that prints out the ASCII, and I run it, you see that it's going to be fetching an instruction from memory, and then it's going to be decoding it to understand what it does, and then it's executing it using this allocation, and then it's deciding what is the next command to execute. And it's going to do this again and again. This program is going to, what it does, the machine language is, we set x2 to this address in memory, which is where you write out the bytes, and then we set x5 to 32 and x6 to 127, and then we go in a loop. We loop repeatedly. We print out one character to C0. This is a store byte. This is this one. And then we add one to x5. We check if we are, we jump. Okay, we jump here, and we check if x5 is greater than 127, which is the end of the program. If not, we continue running. So there is a condition here. You see, branch if equals. If x5 is equal to x6, we are going to exit the program. We're going to run. This is just an idle loop. We get stuck. And if not, we continue running. And out. Finally, we outputted one thing to x0. And there's a space. You can't see it because 20 in ASCII space. And this keeps on happening. And what I want to show you here is what is called the instruction pipeline. So the CPU is going through a series of stages. First of all, it's fetching the next instruction from memory. Then it's decoding it, trying to understand what this function needs to do. Then it's executing it, doing whatever it needs to do with this function. And finally, it decides which is the next instruction it should run or store the results. This is storing the results. Storing the results and deciding which is the next instruction to run. And you see it's cycling through these programs. It's going through this one after the other. If I turn off the animation, you see it's just printing out the ASCII characters. You turn on the animation once again, and you see it's okay. So now let's try to build a really, really fast processor. Let's go back from this to my slides. Here is a screenshot of this very, very program. This program, which is just printing a series of ASCII characters using the Virgulator. And I want you to be to look at. So now we have 4 steps. We need to fetch. We need to fetch the next instruction from memory. We need to decode it, understand what it does. We need to execute it, and then we need to store the results in the memory once again. So, and we want to make a really, really fast CPU. So what is the way to do this very, very quickly? Something which is very basic computer design. We do what is called pipelining. Pipelining means that while we are decoding one command, we are going to be executing another command. And we're going to be fetching another command. We're going to be storing another command. So in fact, there is like a little arrowhead which is continuing through the program. We're going to be fetching one command, decoding one command, executing one command, and storing one command. And this way we can run much faster. All of the CPUs you know use pipeline. And now I'm going to do an interactive pipelining experience for you. I see that all of your cursors are green. Can anybody choose a different color for the pen? I want to see if your cursors change colors. If not, I'll have a... No, they stay green, right? That's too bad. Okay. No, it's always green. Can I set your color somehow? No, I can't do anything. Okay, it's going to be right. So let's just take let's take 3 volunteers. First people who say something in the chat. First 3 people. Okay, Orel, Lido, and Oria. Hi everybody. Okay, Orel, you are. Excuse me, I need to write something down. Orel, your cursor is going to be. I'll do it. Orel is fetch, and I need to do it probably in the C. Okay. Orel is fetch. No, this is terrible. All of these advanced teaching techniques, right? Awesome. So OL is fetch. And let's say next one is Lido. Lido is decode. And Oria, that's how it's spelled in English? Was it Oria? Okay, Oria. We're going to be execute. And that's enough, okay? So all 3 of you, I've just reset the program. So please place your program counter. So please stand next to the first instruction, right? Oh, you know what? Stand here. You're not running anything yet, okay? Lido and Ria, please stand here. So now I've turned on the computer and it starts running. The first thing it has to do is fetch. So which command is it going to fetch? Right. OL is fetching the first command. Awesome. Right? This is what we can do in this first cycle because we don't know what to do yet. Okay, the next cycle, the next CPU cycle, what you're going to do, you're going to fetch the next instruction. That's great. Now we already have an instruction fetch, so we can decode it. So Lido, you can decode it. But we still can't execute anything. Right? Next thing that happens is the next instruction. Okay, OL is fetching the next instruction. Great. Lido is decoding. OL is fetching the third instruction. Lido is decoding the second instruction. And Oria is finally executing the first instruction. Right. The instruction is a load. Awesome. Next clock cycle. Okay, OL is fetching this first instruction, the fourth instruction. Lido is decoding the third. Oria is executing the second instruction, which is add. And now, Orel, very carefully, we're in cycle number 5. What are you going to do now? What are you going to do? So can you share your dilemma with us, Orel, in the chat? Can you, what instruction are you going to fetch? Do you understand the dilemma here? Okay. Which instruction are you going to fetch in cycle number 5? Please put your cursor next to the instruction you're going to fetch. Okay. So the problem here that instruction number 4 is branch if equal. So branch if equal means that if x5 is equal to x6, you're going to run to this command, actually. You're going to go to this one. If x5 is not equal to x6, you are going to continue to instruction number 5. Do you know right now if x5 is equal to x6, OL? Don't solve the problem. Just tell me. Don't run ahead. We're teaching the entire class now together, me and you. Do you know if x5 is equal to x6? No, you don't know it. Why don't you know it? When will you know if x5 is equal to x6? When will you know it? You'll know it when Uriah executes instruction number 5. Right? So we need to wait. What is called the pipeline stall. The pipeline is stuck. So OL can't fetch anything. So Lido is going to decode this instruction also fine, but Lido can't decode the next instruction either in the next cycle because Lido doesn't know what the next function is. And only after Uriah, 2 cycles later, Uriah executes this one, then we know what the next program counter is, and then the pipeline can start running again. And pipeline stalls are very, very bad because we are stuck again. We can't use our pipeline. We don't know what is the next instruction to fetch. So we're in trouble. Who wants me to explain the problem of pipeline stalls again? Who wants me to explain it again? Okay. I am in shock because this is the first time I'm teaching it using this very new teaching method, which I just found out a few weeks ago. It's really awesome that you understood. Thank you. So the problem with pipeline stall is we don't know what command to run next because there is a conditional here. How do we solve this? How do we solve this? Anybody have an idea? Okay, so Dimitri is saying just make a choice. Orel is saying speculate. Shimon is saying, okay, we're trying to guess. What we're saying is we're going to fetch, we're going to try. There are 2 ways we can go about it. We can either say this could be the next one or this could be the next one. So we're going to fetch one of the 2 branches. We're going to fetch, let's say we're going to fetch this one. Great. No, we can't do both of them. We only have one pipeline. So we fetch the first one, right? And now we decode it, and now we execute it. But can we store the result of this execution? Can we store it? We can't store it. We don't know if it's happened yet, right? We don't know if this command has run properly. And I want to give you a motivation of a terrible, horrible, catastrophic pipeline stall, and that is a cache miss. Remember the caches that I taught you a couple of minutes ago? If we have to go to DRAM, then we have a huge traffic jam in the pipeline because we have to wait 150 cycles to get this Verstinkenden command from the DRAM. So what we do, we try to say, okay, we think that, okay, this is like a for loop. Usually you stay inside the for loop. So we're going to fetch, we're going to decode, we're going to execute, but we cannot store. We cannot store the result. What we do is we put it in what is called a reorder buffer. It's a little data structure in all CPUs, all relatively expensive CPUs, and it's going to wait there. It's going to wait there. Once this result comes back, this comparison comes back, or this access to DRAM comes back, we can see if we were right, then awesome. We saved a lot of time. We just store all the results and we keep on running. What happens if we were wrong? If we guessed wrong, what happens? So yeah, if we guessed wrong, we can just discard all of these instructions. We didn't store them. So we wasted time, but it wasn't time they could have done anything else with anyway. So we don't have to roll back. So Shimon, we don't roll back. We didn't store any of these results. It's not like a transaction memory. But they're all waiting to be executed in the reorder buffer. We just throw away this intermediate calculations, and we just keep on going from the point where we're running. And this is the long and short of speculative execution.